will have 1 hour guest lecture by Gal, and the second hour will be regular lecture and with some discussion about the upcoming quiz next week. Turning back to Gal's talk, a few words about his background. Gal did his PhD at Ben-Gurion University in distributed computing. He's currently a senior researcher at Kamal, the Israel Nuclear Energy something. In addition, is
something very true.
Exactly, filling the blank. In addition, he's an adjunct professor at the CS at the Technion, and on top of that, he's running the Open MP.
One API Center of Excellence.
Something API Excellence by Intel. And he's going to, the reason I asked him to give, and on top of that, he's collaborating with me on computer vision, deep learning stuff. So he's a very distributed person. The goal of this lecture is to show you that what you're learning here is just the beginning of the journey. It's by no means the end. And Gal is at the forefront of how do you design computers to solve real hardware problems. And that's what he's going to show us today. Gal, the floor is yours.
Thank you very much. So under this very detailed presentation, I have very few words to continue, but let's do it. So today's topic is really a brief, gentle introduction to the topic of parallel computing. Actually, you will see that most of parallel computing today is centered around supercomputing of the past, not that far past, but actually the near past. And it's mostly helpful for supercomputing that we have today in any kind of hardware that we have, and any kind of application that we have today actually do parallel computing. So it's like some kind of there is a lot of relationships between those terms. So what we are going to talk today, we're going to talk about, as far as I will be able to continue. But first of all, about the why doing multi-core, why doing parallel computing. Afterwards, we will talk about the advances of parallel computing with a single core, which is approximately where you are in the course right now. I know you don't talk about parallel computing yet, but you do talk about a single processor. So what we can do with multiple of those single processors. Afterwards, we will talk about the invention of multi-core, the thing that you actually have in any kind of chip today. There is no single core machines anymore. Then about non-uniform memory access, meaning how this change in multi-core changes memory as well, which is not the same, is not uniform as you can imagine. We will somehow try to understand how we all of those can collaborate either in the cluster or the cloud, how they contribute to supercomputing. What is many-core? The last trend that is enabling all of the AI and dense computations that we have in the since 2013, and where it takes us to exascale, meaning what is the scale of the computations that we can do today. So with a lot of exposition, let's start with the why. So I would like to start with this piece of hardware, which is not actually digital. It's from 2600 before counting. And that's actually the first hardware that was part of a parallel computation. It was found in Sumerian, and actually I got a chance to go to the Pergamon Museum in Berlin to see it by myself. And I saw a lot of those pieces, which back in today's Iraq, used to do calculations of the area of agricultural fields by many people, many agricultures at the same time. They used those hardwares as some kind of a calculator, and with distributing them to all of the agricultures and collecting back the results, we could understand what is the actual size that we have, what is the actual size of the land that we have. So that's the first part that we know of parallel computing. Well, obviously, there was a lot of advances since that sub-flop area, flop, meaning floating point operation per second. Obviously, that hardware is not floating point, as you just learned in the course. Floating point came afterwards. And we see that there is a lot of analog and semi-digital and digital hardware, and afterwards supercomputers, clusters and supercomputers that enabled us to increase the amount of computations that we get from a single machine, meaning how many flops, floating point operations per second, we can achieve, we can extract from those machines. We started back then from DESI, and now we are in the peta and exascale. Petascale, exascale, look at the words very carefully. It's 3 orders of magnitude between those two terms. But exascale, the first exascale supercomputer just landed in June in one of the American national laboratories. And it means that it can do 10 to the 18th floating point operations per second. Just try to imagine that number. So what we do with all of that parallel computing, actually we do what the people in Samaria did back then. We understood that there are problems that need to, they have special locality, they have, they depend on time, and we want to do a lot of steps in the calculation of those problems in order to get to the final results. We see that in weather, we see that in climate change, but we also can see that in many hardware that is not for computers. For example, engines, brain science. We can see that in all types of industrial and commercial uses. Any kind of airplane that you currently take to Europe or to probably to America. The 787 was completely simulated by a computer before a cluster before it actually even been built. So we understand that the power of parallel computers and parallel computing enables all of those advances over time. So when we consider a single core, we see that we have instruction, we have a problem like the problems from before, like the car or the climate computation. And we have lots of instructions that we need to do, and we feed those to a processor, right? In parallel computing, we would like to do that in parallel. We would like to feed those processors with instructions in parallel. Now, if it was that simple, we would stop the presentation at this slide. Obviously, this is not what's happening. But let's go back for 1 second to the von Neumann architecture that I believe that you're already familiar with. So von Neumann understood that in order for a CPU to work, in order to computing to advance not in a static fashion, we need to have a control unit, something that says what to do, the ALU, something that says how to calculate, and feeding those input outputs and have some kind of memory. Now that's great for serial. Someone else just afterwards in 1966, which its name Flynn, came up with a taxonomy that says, okay, if we have that one processor, what are the fashions that we have for parallel computing with that processor, with this processor that have instructions and have data? So he found that there are 4 types of computations even before parallel computers were even there. So we have the single instruction, single data, the single instruction, multiple data. We have the third multiple instruction, single data that does not actually exist in reality, and multiple instruction, multiple data. Now, single instruction, single data, it's the CPU that you are very familiar with. The single instruction, multiple data, it's more like the first computers that have been invented, like the Univac, which is a very large calculator. Okay, it needs to be fed with a lot of data, do those computations in parallel, but all of that time it's like taking a vector in this slide, like taking a vector, divide it, and do all of those parts in parallel. So it's not exactly a parallel computer. A real parallel computer would be a multiple instructions, multiple data, meaning that we have lots of things that happen with lots of data simultaneously. And that takes us to cluster computers. Okay, so we briefly talked about what we can do in parallel with a single CPU. You're obviously familiar with Moore's law, right? Moore's law said It's a industry law, not a natural law, that says from many years ago, that says from back to 1965, right? Like Flynn taxonomy from 66, says that every 2 years or so, something like that, the number of transistors on a semiconductor device, a chip, will double. Now, this law enabled us to yield more and more computations from the increase of the amount of transistor in a single core, in a single CPU, which is great, because if that progression could be made eternally, we wouldn't really need to do lots of changes in parallel computing. We could just feed a lot of machines simultaneously, and that's it. And we can see in this graph that those processors over time really stood to the trend, meaning that over time they really doubled the amount of transistors. And we can see also in the trends here, besides what is in red, that the performance that we get from the increase of transistors in that single chip really gave us a correlated double performances in comparison to the previous generation. The problem is not with Moore's law. Moore's law is not a real law. It's not a real law. The problem is that physics have another idea about how chips could be placed on a single chip. And what we can see in the end of the trends here, something around 2005, we see that the growth in performance in comparison to the amount of transistors that we put on the single chip is not going linearly as the fashion that we were used to with all of the hardware that we got in the past. That's called Dennard scaling, or the depth of Dennard scaling. Dennard scaling is another physical law that is an actual law. That said, it's also an observatory law, meaning that it's not a natural law. It says that if we could put more and more transistors on a single hardware, and those transistors get smaller, now they need less voltage. And if they need less voltage, it means that we can drive the entire chips faster with frequency and do more computations. And if we can do all of that circle, it means that we can put more transistors and get more performances. Now, that was true up to 2005. And all of a sudden, sharply, there was a change. And that change caused from multiple factors in physics, but we will not elaborate on that right now. But that change happened somewhere in 2005, and we see that with the reduction in the size of those transistors and putting them on the same hardware chip in size, the same size of the hardware chip, we need more and more power in order to drive the performances to a new level. And we can see that in more depth here. We see that since that around Pentium 4, we see that in order to extract this amount of performances, we need to put almost a squared amount of power in order to get that. Now, that is a growth which is unsustainable in any way. We cannot do that. We cannot feed those hardware with that amount of energy, because we're gonna get memory leakage. We're gonna get transistor leakage. We're gonna get leakage at any kind of scale. And it's not gonna work. It's not that we could push more power and it's gonna work in the same way. It wouldn't work. And what we can see in this amazing graph by Carl Wu is a collection. Each point here represents some sort of a CPU, a real CPU, not an imaginary one. And we can see the change that happened in reality because of the end of Dennard scaling and the change in performances. We can see that somewhere around 2005, we moved from this single core thinking, and we increased the number of cores. We see that Moore's law didn't stop, right? We see that we have more and more transistors over one chip, but we also see that the frequency and the power that we feed those chips stays approximately the same. And we see that the amount of performances that we extract from those machines is very mild now. It's not rapid as we got before. And any of you that will check his computer right now and its computer from 10 years ago and go to the specs of the computer will see that most of the hardware today runs in around 2, maybe 3 gigahertz frequency, and this is not changing. We are not getting more of the hardware. Now, why is that? Why is that specifically? What actually happened? So remember this very simple equation. This equation says simply that the power that we need for those chips equals to the capacitance. The capacitance is the ability of a circuit to hold that energy, times voltage square times the frequency. Now, if we will look on a single core, single CPU, meaning a CPU that have one core on it, and drives with a capacitance of C and a voltage of V and a frequency of F, we will get C times voltage square times F. Now, that also explains why we cannot actually drive more voltage in there, because voltage is squared. If we will do some trick and we will divide on the same chip, we will divide the amount of cores. We will keep the capacitance, the accumulated capacitance the same, but we will drive the chip with half of the voltage and half of the frequency. We will get only 40% of the power that we need to put in this chip, and we get the same results, even better results, even better performances that we got from a single chip. And that's why the computers today don't look like a CPU that is attached to one piece of memory. It looks like that. And that monster is a one CPU. That's a CPU today. It's not the CPU that, as you can see in the book that we currently read, that's a CPU. It has many cores. It has different types of memories, different interconnects, and it's very complicated. In many ways, it's very complicated. If we will look on the list, I'm trying to convince you that this is really a trend, and it's actually happening in reality. If we look on the list that's called Top 500, which is a list that represents the architecture and the performances of the top 500 supercomputers today, this is not from today, this is from June, we can see that this kind of processors like the Xeon Gold and the AMD ROM and things like that are very familiar with the architecture that I just presented, those are ruling parallel computing. So we use that all the time in parallel computing. So I just presented how the change in the reality of power and the reality of performances changed us, moved us from single core to multi-core. But what actually happened to memory in this transition? We talked only about transistors, right? So if we will look on the board that we just saw before, we see that there is a lot of CPUs, small CPUs, PUs, that are attached to memory are be fed by it. Now, the memory itself, even the memory itself is not the same as it used to be. Today, we see that the memory pyramid hierarchy changed. We have more cache hierarchy. We have high bandwidth memory. We have also persistent memory. We have different types of memory. We have flash storage. We have flash storage that is byte addressable, and we get all those types of memory that are attached to those different to the different types of accesses in the CPU. So in order to exploit all of that differences in memory, we see that a current typical CPU that, like we saw before, has a lot of access to memory. The memory is not flat as it used to be. And each CPU in each some Euclidean space has an access which is not uniform to different types of memory, from the L1 and L2 that is attached to it, to the L3 that is somehow divided between portion of the cores, to the DRAM that is attached to a single socket, and even to a DRAM that is attached to another socket. And all of that memory is somehow on a single address space. So that's very new. That's not like we used to have in single processors CPUs. If you would like to see the change, the dramatic change of the cost that we have between those memories, we can see here in this graph, we can see that in relate to this socket architecture, the cost of one CPU here to get to the memory that is attached to a CPU here, the 0 to 3, is much larger than the cost of that CPU memory access to a CPU memory access in the other socket here, the number 1 socket. And that's actually because the memory is disaggregated, is not the same, it's not uniformed anymore. So all of that changes that we have now a lot of cores and we have a lot of memory, and all of those disaggregated on a single board, on a single chip, give rise to the threads model. The threads model, I'm not sure if they're familiar with it. Okay, the threads model says that instead of controlling the entire hardware without understanding what there is in it, we can work in a different fashion and think of how we get a full control of the device, and understand how we can control the device without being without believing that we see a single CPU. That's the thread model. I'm trying to somehow reflect that I understand that you are not familiar with the model and trying to translate somehow. So it means that we do computation that is aware of the hardware beneath it. That's the change. That's the thread model. And we can see that over time in this top 500 chart, we can see that over time more and more cores are attached to a single L3 cache block in all of those supercomputers, meaning that as time progresses, we see that more cores are attached to the same piece of memory, this L3 memory. Okay, so now we understood that those new computers have many cores and their memory is disaggregated, and there is new fashions of how to operate them, how to see them from the inside, like thread model, how we can collaborate the efforts that each and every one of those do in order to have a larger computation, in order to have more performances. So let's start from the beginning in this case. What we actually want to do in cluster and in cloud computing. What we want to do is to solve a problem that we can, first of all, divide its domain to parts that can fit on different computers. We understand that we need to somehow collaborate all of those computers that don't have the same memory space and don't have cores on the same chip, and we need somehow to put one single problem on all of those and use all of those synchronously combined. So first of all, we take that domain and we partition it. That's called domain decomposition. When we partition it, we can see that, let's see if it works. Whoop. So when we partition the domain, in this case, it's solving the Laplace equation, we can solve each part of the domain separately, somehow find a way to communicate around the borders of the problem, and only there. And afterwards, to get the entire solution and return it to one one computer. We can do that also functionally by saying that, for example, in many models, we say that there is not a single program. We have different models in the program that have some kind of interfaces. And in this example, the climate model program. So we see that there is interfaces between different types of models, the ocean model, the land, the surface, the hydrology, and each of those models is put on different computer. So if we would like to make one problem to be divided over all of those computers together, we need to find a good network to combine them and synchronize them all of the time. Now, that network should be extremely fast because it needs to be fast as the interconnects that we have in the chip itself, right? So that's the reason why parallel computers today actually also changed from over the last 10 years and support something that we call RDMA. RDMA means Remote Direct Memory Access. One company here in Yokneam, 23 years ago, understood that slide very well, and they called Mellanox. They developed the InfiniBand fabric, and that InfiniBand fabric from Yokneam is the fabric that actually supports all of that synchronization between computers all around the world. That's the reason why NVIDIA, for example, bought them just a year ago. So we can see here again in the top 500 list, if we want to divide those computers by the fabric that aggregates the hardware, we see that InfiniBand is very important. We also see Ethernet in many other computers, and the reason for that is that also Ethernet got very fast in bandwidth, in latency, and there are a lot of computations that can rely only on bandwidth. Inversely parallel computations that don't really need to synchronize everything all the time, but need a lot of bandwidth, can work with gigabit Ethernet, and not with InfiniBand. So let's see how one cluster like that looks like. So we can see here lots of blades. In each blade, we have those CPUs on it, this non-uniform memory access on it. We see that in each rack, we have an InfiniBand switch. That switch support, it's a computer, supposed to connect the other racks to the management of the entire machine, and one to another. And by that we get this cluster computing. Cluster computing is not, in today's terms, since like 3-4 years ago, cluster computing is not only presented in one big machine that is deployed in one single space. The cloud thinking changed all of that, and how that actually been made. Think of that we have the internet today, and for example, Amazon Web Services and Google, they have lots of computing power that is being spread all around the world, and you can ask logically to get all of those resources somehow to make them to be logically one piece of hardware, and put your calculation on this imaginary hardware. Now, it's obviously not going to work, as you probably just understood. It's not going to work like a real cluster, because if the fabric is not supported, if it's not a 1 microsecond latency fabric, you cannot run real synchronous computation there. But are all of the parallel computations need to be synchronous? No. Think of a Monte Carlo computation. Think of many inversely parallel computations. Means that those computations don't really need to talk. We need to just do a lot of labor without synchronization. So for those purposes, the cloud is very good. We can also see a trend in the cloud that each instance, each compute node, each one single hardware have a lot of more CPUs, more memory, more performances on a single chip because they understand that the fabric cannot support the performances that people want to get. So we need to somehow extract more performances locally, not distributed. Okay, so after we understood what cluster and cloud are, what are the difference between just a simple cluster and a supercomputer? First of all, let's understand what a supercomputer is. Supercomputer is firstly a cluster. It has to be a cluster. So it's supercomputer in a Venn diagram. Cluster is inside the term of supercomputer, but it's not completely correlate to a cluster. So what actually supercomputers are? They big machines that tries to get more and more performances, but they want to do that for specific applications, not for general purpose applications like regular computers, not like regular clusters. They do so for specific applications. And that's the reason why we can find those machines in national laboratories, in specialized groups, in big companies that tailor-made their cluster to solve specific problem. Now, what we see in this table is area of science and the main kernels that we use in these sciences. And we see that each of those kernels, like dense linear algebra, sparse, structured grids, and so forth, is correlated directly with some kind of bounds of the hardware that we just talked today. Meaning that each part of the single cluster that we have is combined, has a lot of bounds on each part of the combined parts of the system. Either it's a bound on the latency, either it's a bound on the bandwidth of the fabric, either it's a bound on the amount of flops that we need to get, either it's a bound on the amount of storage, the IOs that the program is doing. And by that we understand that supercomputers mostly been built for specific applications with specific bounds in a single program. Meaning that in most of those supercomputers, we will see that in most of the time, a single program runs there. I can give you an example from the Middle East. Aramco from Saudi Arabia have the number 8 supercomputer in the world, number 8 ranked supercomputer in the world, and that computer mostly and solely solve equations that somehow help them to discover new oil fields. That's what this supercomputer does. So I don't know if there are microphones. Not sure. So I'm going to skip this video. This takes us. We have 15 minutes, so it's good. I'm on track. This takes us to many core. So we just finished talking about supercomputing, and we thought that this is going to be the end of the lecture. But if we reflect for 1 second on what we just talked, we see that there is not a real growth over time in computation from those single processor machines. We see that the Nernst scaling actually ended. We see that Moore's law is not progressing as we used to believe, as we used to think. For example, right now the movement is from 7 nanometers transistors to 5 nanometer transistors, and there is a big dispute between the head of NVIDIA and the head of Intel. Either Moore's law is dead or not. Meaning, either we will be able to create the 3rd nanometer transistors, and there is a belief in the industry that the 5 nanometer is the end of that scaling, and there is no need to do more than that. So how we got better and better supercomputers over time. How we can somehow remember this trend? We see that those large machines still keep track with the needs of performances, like Moore's law still exists. We get those performance increases with the many-core hardware in differ with the multi-core that we just talked before. Before we talked about a single chip that have multi-cores. It's the same thinking, but multi. Many-core, like the GPU that runs all of the AI computations that you are familiar with, it's kind of different. It has the following agenda. Let's put a lot of small cores on a single machine. Let's put very high-speed memory attached to this hardware, and let's drive the entire this entire piece of hardware with a lower frequency than a CPU. So we immediately understand that regular programs cannot run on this kind of board. So, I mean, most of our programs are not really massively parallel. They are not looking like a matrix that we can put on it. We don't have data structures that actually can fit perfectly on that kind of machine. And we don't do only math on computers. We do a lot of branching. We do if, else, while loops, things like that that are not computers, right? So this kind of hardware created a new taxonomy in the 1966 Flynn taxonomy of how parallel computing actually works, and defined the new single instruction multiple threads, meaning softwares that are being written in a perspective of lots of micro programs that run simultaneously, concurrently on one machine and do a lot of work collaboratively. This is a special case of parallel computing and a special case of parallel hardware that enables to take all of the problems of Dennard scaling and all of the problems that we got with Moore's law and almost eliminate those. Because as we run with more hardware, with more threads, with more cores, extremely with more cores, that kind of machine can have 10,000 cores on one piece. So we understand that we can get much more performances, but only very specific kind of computations can run on it. In a state-of-the-art supercomputer, for example, the Frontier that just been launched in June, it's the first exascale supercomputer in the world, the first and the only for now, and it's placed in Oak Ridge. It's a national laboratory under the Department of Energy in the US. Each kind of a rack like this have 128 nodes, 128 blades. In each blade, like you see on the right, we have tons of memory, disaggregated memory, non-uniform memory accessed memory, tons of CPUs, and lots of GPUs. All of the left that you see, I'm going to increase that. You can see that over here. Most of the hardware is actually an accelerator, not a CPU. So the thinking goes like that. We will control all of the operations that we need to do from the CPU. The CPU is the brain behind the local computation in each blade, and it will feed the different GPUs on that board with the actual computations that we need to do. That's the mind shift that we got over the, I don't know, 5-7 years in supercomputers. That's the way to increase those computations. Now, obviously, those codes are not even similar in any way to the codes that we are regular to see. Meaning, for example, in OpenCL and CUDA, we orient the code around functions, and each functions run separately on a single on a single core. Now, this is a type of design pattern that you will never see in a regular code. You can see that something like that. It's not even linear in the thinking. It's parallel inherently. And in order to make all of those hardware to work collaboratively, the CPUs, the GPUs, the disaggregated memory, the RDMA network, there is a need for different types of parallel platforms in order to make that work, because each hardware works with a different parallel platform. Finally, I'm concluding, it takes us to exascale. Now, I just talked before about that frontier is an exascale computing, right? Look on that monster. That monster is the Aurora supercomputer. It's supposed to be launched at the beginning of, it's probably going to be in June of the next year. This monster is already more than 2 exaflops. 2 exaflops. More than 2 exaflops. It fills, I think, something around 10 soccer fields. Yeah, thank you. And in each of those hardware, we see the same trend that we just talked about in the previous computer, and we see that even the cooling of those hardware is not even based on air anymore. The cooling that we get for those machines, which are completely dense, that's extremely dense, we need to put the water actually directly on the chip in order to evacuate all of the heat that we get. So that's the last frontier in the definition of what a supercomputer is, because in the future, we will not even see supercomputers that are designed with air cooling, because air cannot cool those machines anymore. And that's a new philosophy in supercomputing. In this chart for computing, I'm presenting that in a single GPU, a new Intel GPU that has been called Ponte Vecchio or a Max GPU, we see that the amount of performances that we get from that single CPU, from that single piece of hardware, is equivalent to the top supercomputer, not from 1966, from the year of 2000. That's how dramatic the change is. You will see that from those videos. So to conclude, we reached the end of the presentation. I really wanted to give you a taste of the changes that we have today in parallel hardware and software, and where it takes us. We covered why we need this kind of parallel computing and supercomputing, what we can get from a single core, why this is not enough, and we move to multi-core, what happened to memory, how all of those can be accumulated to a cluster and even a cluster on the cloud. What is the difference between a cluster and a supercomputer? How many core changed the field of computing entirely over the last 10 years? And what is the new frontier? What is the new frontier in supercomputing, which is exascale? And all of those points collaboratively gives us the notion that state-of-the-art, new, modern programs that actually run on a real hardware today is based on, obviously, on the algorithm and the data as we used to think all of the time. But in today's terminology, we know that the hardware is an imminent part of the design that we need to take care of, and it's not transparent anymore to us as programmers, users, and researchers. And by that, I'm concluding. Thank you. Questions? Questions? Yes.
I have a question.
Sure.
So, what's the role of the program? we teach students here to program in C. But is there a parallel C thing, and how do you who do you think is going to split the best out of the machine? The compiler that takes your C and feeds it to the hardware, or do you think that the programmer needs to better understand, if so, better understand the hardware and then redesign its code? And if so, what do they have to do?
So it's 3 questions, right? Now let's start from the end. The responsibility is of the user, the compiler, and the hardware. All of that combined. Let's explain. First of all, C, Fortran, and C++ are the main languages that supports high-performance computing. We need to remember that. We need to remember that while we currently learn Java or Python and things like that, all of that underneath it's C code or even Fortran code. In real supercomputers, people work with Fortran. Why? Because Fortran have more performances per numerical operation. And Fortran is since 1966, and it's still with us. Because what you teach right now in your course didn't change in this regard. The mantissa is the same, floating point is the same. So getting those performances from a single computation, from a single line, is the same. What actually changed is how we use these languages in parallel. Now, in this case, first of all, compilers do a lot of work. Compilers, either Intel's ones and others, do a lot of work in order to make those CPUs being fed with more data and instructions all the time without us doing anything. But that's not enough. And they don't really know how to parallel a code, because the parallelization of the code is inherent to a specific type of program, and it's not a global. There is no global thinking in parallelization, and it's been done in two ways. The first way is to change the code entirely and make that code to be thread or process oriented. CUDA, for example, is doing exactly that. You take a code and you change it completely in order to make it run with multiple threads. But the new notion is that most of the actual codes that you will want to run, besides AI and dense linear algebra, to run on that kind of computers is not CUDA based, is not looking like CUDA. And you need to take regular code and somehow instruct the compiler to do more. And if you will instruct the compiler regarding the structured block that you have underneath that instruction to do this differently, you will get more performances. That's called OpenMP, and that's exactly what I'm teaching in the Technion. That's the course topic. We learned there how to do that manually, how to change code manually, but with small adjustments in order to fit new hardware. Did I answer all of those? Go ahead. Yes.
Okay, so of course we talked about how the grain of the operation on a single process is component. And in your lecture, you said that in hybrid architecture with GPUs, the CPU itself takes the leadership as the brain of the processor.
Not only the CPU. You see that even in the hardware it changes, in the software it changes, the hierarchy changes, and all of those changes make the notion that as you take more and more hardware, there is no single commander. The single commander is somewhere there. It's with one process that only initiates a hierarchy of commanders. It's like forming an army instead of thinking that we have only one soldier in this battle to get more performances. So in multi-core, the difference is that obviously each core has its own ALU and its own instructions, but you understand that the memory in this von Neumann architecture, I'm going back to the von Neumann, 1 second. If we look on this slide, we see that the memory completely disaggregated, right? Now, the L3 level is shared with others. Now, if it's shared with others, obviously your instructions can harm the instructions of another core. And that we call concurrent computing, how we actually make those instructions not to be dependent on each other and to work simultaneously. That's a whole field to make those programs work correctly. And you see that the input and output changed, right? Because we can get that from multi-channels, right? And we see that the instructions that we get that the ALU has been fed with is not coming only from the control heads. It can come from other places as well. So everything changes. I think that the real title of this presentation could be everything changed from what you currently learn. But still, what you learn is the building block of everything that we currently see. So that's the other side of this coin.
Saying that there is one management, like
there is a management. Obviously, there is a management. There is a synchronization. But this synchronization is not of a single commander. Yes.
You presented like the effort that is being made to make computers, which are usually like huge subscribe, and also require resources that only like in a national scale, like economic giants have. But what is the effort in terms of like parallel computing that is being made? I don't know, to feed to our regular, let's say, operas, computers, or
it's not. I understand.
I'm assuming that low is that.
So it's a great question, and I think that I answered that only with few words in the presentation. But the thing is that as we see the progression of parallel computing and parallel programming over time and its reflection on supercomputers, because it's easy to see it over there. If we go back to the multi-core transition, we see that every kind of hardware that we have is multi-core right now, right? Your phone is multi-core. And if your phone is multi-core, it means that the same paradigms and the same thinking that we have in a supercomputer, you have that on your phone as well.
Yes, but it's small.
Right. But small is not I mean that the fact that it's small, it don't say that it's different. It's not different. It's very much the same. If you look on an iPhone, you will see all of the parts that I just talked about completely on the board. You will see that you have a specialized many core chip designed specifically for dense computations over the camera, and you see that you have multi-core for CPU, because if you want to browse many pages in Safari at the same time, you need to do those synchronously over many CPUs. That's the way we have multiple applications at the same time. Because if we didn't have that on our iPhone, we could use only one.
I understand that like it's bounded. Like supercomputer always can take more area and add more computers. In our phones, we are bounded by its size. So
right. That's true. That's true, but there is a change. There is a difference between supercomputers and an iPhone in this regard. As you said, people, governments, companies build supercomputers for a specific task, because they know that parallel computing and computing in general have lots of bounds on the different parts that you have there. And if you want to have an AI supercomputer, it's going to be very much different from a climate supercomputer, okay? Because an AI supercomputer like Facebook's supercomputer is going to do a lot of ray tracing, for example, in order to do these twin worlds in Meta, right? But it's not the same. It's not going to work very well for climate, because climate do a lot of simultaneous work which is not dense like this one. So you see similarities, but you also can understand that there is a lot of dissimilarities between those systems. And by that